In today's interconnected world, protecting digital assets is paramount for every business. This course provides a foundational understanding of IT security concepts and their critical role in safeguarding our organization's data, systems, and operations. This is Chapter 7 of a larger course titled Introduction to Information Technology. Let's look at what we are about to cover. We will start by understanding the core principles of protecting business data and systems, including the CIA Triad and the AAA Framework. Next, we will learn how organizations manage who has access to what resources within their systems. After that, we will identify the typical cyber attacks that businesses need to be aware of and defend against. We will then examine the strategies and tools that are used to secure a company's network infrastructure. Finally, we will delve into the fundamental science behind securing communication and protection of data. IT security is about protecting your business's data, systems, and networks from unauthorized access, cyber attacks, and other potential threats. The goal is to maintain the confidentiality, integrity, and availability of information, commonly known as the CIA Triad. The core principles of IT security are built around the concept of AAA. The first A is authentication. This is verifying the identity of users before granting them access. It could be as simple as using a username and password, or more advanced like biometric scanning, an example being fingerprints. Once users are authenticated, we grant them access only to the resources they need. For example, an employee in the HR department might only have access to HR files, but not financial records. And lastly, accounting involves tracking what users do within the system to detect and respond to any suspicious behavior. For example, keeping the log records of who last accessed and modified a file folder. So let's see how these three concepts work together. Imagine you're an HR employee logging into the company's ERP system. First, you authenticate by entering your username and password. Once logged in, authorization ensures that you can only access the HR module and not other departments like finance or accounting. Finally, any actions you take within the HR module, such as updating employee records, are recorded through accounting, ensuring all activity is tracked and logged. Let's talk about identity and access management, or IAM for short. IAM is all about making sure that the right people, and only the right people, can access the right resources at the right time. It is a combination of policies, technologies, and processes that help organizations manage who can access what. IAM covers several things, such as authentication, which is verifying identity, authorization, which is deciding what access someone has, and the lifecycle of tasks, like account provisioning when someone joins and deprovisioning when they leave. In IAM, an identity isn't just a name. It's a digital representation of a user, device, or even an application. It helps the system understand who or what is requesting access. One of the most widely used IAM tools in organizations is Active Directory or AD. Think of AD as a digital phone book and security gate rolled into one. It stores user information, manages group memberships, and controls what resources each user can access. Let's look at what happens behind the scenes when a new employee joins. The IT team creates a user account in Active Directory. This is called provisioning. The account includes a username and login credentials, department and job title, membership in certain groups. Now these groups are important. They control access to different systems. For example, someone in HR gets access to HR software, but not the finance database. This is known as role-based access control or RBAC. And we could define these roles based on job responsibilities and assign access accordingly. Every user account in AD is part of a domain, which acts as a centralized identity store that manages users, devices, and permissions. Once the account is active, the new employee can log into company computers, email, and internal applications using their AD credentials. They don't need separate passwords for every system because authentication is centralized through AD. So let's see what happens when this employee tries to log into SQL Server Management Studio or SSMS. They don't have to type in a separate username or password. They just use Windows authentication, which means their identity is automatically verified by AD since they're already logged in. Here's what's happening behind the scenes. SSMS asks AD if this user is valid. AD says yes, they are. And that's authentication, verifying who they are. But that's only half of the story. What the employee can do inside SSMS, like reading or updating data, is governed by authorization. That depends on the employee's Active Directory group and also their assigned database roles in SQL Server. So authentication gets them in the door and authorization decides what rooms they're allowed to enter. Now Windows authentication is convenient, but it still depends on the employee using a company-issued device and logging in through the company network. Single sign-on or SSO takes things further. With SSO, we sign in once, and that login can work across multiple systems. This is especially helpful in modern cloud environments. If our company uses Azure AD SSO, we can sign in once and access apps like Azure Data Studio, Power BI with no repeated logins needed. This way is more secure and more convenient. The key here is that SSO allows cross-application access within the same domain. Now this is great, but what happens when we work with other organizations such as vendors, partners, or subsidiaries? That's where federation comes in. Federation lets users from one organization access systems in another without creating new accounts for each system. It's the foundation of what we call Federation Identity Management or FIM. Here's how it works. Our company acts as the identity provider. This is a system that manages our login and credentials. Examples of IDPs include Microsoft Entra ID, formerly Azure AD, and the partner company will run a service provider, which is an application or service we want to access like Salesforce, Workday, or even a shared cloud portal. So in this scenario, we are the external party trying to log in into our partner company's internal system. When we attempt to log into Salesforce, our identity provider authenticates us and then passes that trusted identity to the service provider. Since the two systems trust each other through a federation agreement, we don't need a separate login for Salesforce. Our existing credentials work. This kind of setup makes collaboration smooth while maintaining strong security and identity control across organizational boundaries. Now that we understand how federation identity management works, the next question is, how does this actually happen behind the scenes? That's where identity protocols like SAML and OAuth come in. SAML is one of the most widely used protocols in enterprise environments. This is especially common in single sign-on and federation scenarios involving web applications. Let's see how SAML works. First, a user attempts to access a cloud-based service, which is the service provider, such as Salesforce. The service provider redirects the user to their organization's identity provider for authentication. The user authenticates with their corporate identity system, typically by logging into the IDP or identity provider. Upon successful authentication, the IDP sends a SAML assertion, which is a secure XML message that confirms, yes, this user is who they say they are. This assertion is sent back to the service provider. The service provider then validates the SAML assertion and grants the user access to the requested service without requiring further login credentials. This all happens behind the scenes and it only takes a second or two. Now let's look at OAuth, which stands for Open Authorization. Unlike SAML, which focuses on authentication, OAuth is designed for authorization, which is granting limited access to resources without exposing user credentials. While SAML is mostly used for SSO in browser-based enterprise apps, modern cloud services, especially mobile apps and APIs, tend to use OAuth. So OAuth is a bit different. It's not just about logging in, it's about delegating access. And here's the core idea. Instead of sharing a password, we authorize an app to access specific data or functionality in another system. So for example, we might allow Power BI to pull data from a Google Analytics account without sharing our Google password. And OAuth enables this by issuing access tokens, which are secure, time-limited tokens that define what the app can and cannot do. To make OAuth work for user authentication and not just app access, it is often used along with an extension called OpenID Connect or OIDC. So when we hear the terms OAuth login or sign in with Google, that's actually OAuth plus the OpenID Connect in action. Now at this point, we have seen how identity is managed, how access is granted across systems, and how protocols like SAML and OAuth help facilitate trusted authentication. But there is still one critical piece we haven't covered yet. How do we make sure that the person logging in really is who they say they are, especially if passwords can be leaked or stolen? That's where multi-factor authentication, or MFA, comes in. MFA is a security measure that requires users to present more than one form of verification before gaining access to a system or application. It is based on the idea that even if one factor, like a password, is compromised, the attacker still can't get in without another factor. MFA is built around three types of factors: something you know, such as a password or PIN; something you have, like a smartphone app, for example, Microsoft Authenticator, a hardware token, or a smart card; and something you are, which can be biometrics such as a fingerprint, retina scan, or facial recognition. A secure login requires two of these factors. That's why it's often called 2FA or two-factor authentication. And MFA is just a broader term when more than two factors are used or supported. Let's look at a real-world example. Let's say an employee wants to log into Office 365. They enter their password, which is something they know. Immediately after, they get a notification on the Microsoft Authenticator app on their phone, which is something they have, asking them to approve the login. So even if someone steals that employee's password, they won't get in without access to the mobile device. This simple step drastically reduces the risk of unauthorized access, especially from phishing attacks or password reuse. Now that we have covered how businesses control access and verify identities, let's look at the flip side, which is what they are protecting against. In today's connected world, security threats are constant, evolving, and often designed to exploit human behavior. Below are some of the most common threats that modern businesses face and how they work. First, we have malware. Malware is malicious software designed to disrupt, damage, or gain unauthorized access to a system. Common types include viruses and worms, which are just self-replicating programs that infect computers and spread across networks. There is spyware, which is software that secretly monitors a user's activities to steal confidential information. And we have ransomware, which encrypts files or locks systems, demanding a ransom for decryption. Malware is often spread through email attachments, infected websites, or unsecure downloads. And how can we prevent it? We can install antivirus and endpoint security software to detect threats, regularly update and patch operating systems and applications, and implement regular backups to restore data, making ransomware irrelevant. There is phishing. Phishing is a type of social engineering attack where cybercriminals trick users into revealing sensitive information such as login credentials, financial details, or personal data. Let's see how this works. Attackers send deceptive emails, text messages, or fake websites that may appear to come from trusted sources like banks, colleagues, or service providers. The message often urges users to click a malicious link or open an infected attachment, leading to credential theft or malware installation. To prevent this, we can train employees to recognize phishing emails. So for example, checking the sender's addresses and looking for suspicious links. We can use email filtering and anti-phishing software to block fraudulent messages, and enable multi-factor authentication to add an extra layer of security. There are insider threats. Insider threats occur when employees, contractors, or business partners intentionally or accidentally cause security breaches. These threats are particularly dangerous because insiders already have access to company systems and data. Types of insider threats include malicious insiders. So these are employees who steal, leak, or misuse sensitive data for financial gain or any other purpose. And we have negligent insiders, who are employees who unintentionally expose data through weak passwords, misconfigurations, or falling for phishing attacks. To prevent these, we need to implement strict access control, such as the principle of least privilege, conduct background checks before hiring employees in sensitive roles, use user behavior analytics to detect unusual activity, and revoke access immediately when employees leave the company. Another type of attack is distributed denial of service attacks, or DDoS. A DDoS attack overwhelms a website, server, or network with massive amounts of fake traffic, making it inaccessible to legitimate users. Attackers use a network of infected devices called botnets to flood a company's website with traffic, and the following overload on the servers can cause slowdowns or complete shutdowns, impacting business operations. To prevent these, we could use DDoS protection services such as Cloudflare, implement rate limiting to control incoming traffic, and monitor network activity for unusual spikes in traffic. Now that we have explored user authentication and identity management, let's turn our attention to something broader: the security of the network itself. Network security refers to the strategies, technologies, and processes used to protect an organization's network infrastructure. It involves implementing security measures to prevent unauthorized access, detect potential threats, and ensure that data flows safely between systems. Effective network security is crucial for maintaining the CIA of business information. Network security works in layers, each providing a different level of defense. Let's break down the most common essential tools and practices. We have firewalls. These are our first line of defense. Firewalls act like gatekeepers. They examine incoming and outgoing network traffic and decide what to allow or block based on a set of rules. We have intrusion detection and prevention systems, or IDPS. IDPS constantly scan the network for suspicious or malicious activity. IDS alerts you when something looks off. And IPS takes it a step further by actively blocking the threat. We have virtual private networks, or VPNs. VPNs allow employees to securely connect to the corporate network when working remotely. They create an encrypted tunnel between the user and the organization's resources. There is Network Access Control, or NAC. NAC ensures that only the authorized and secure devices can connect to the network. If your laptop does not have up-to-date antivirus, for example, it may be blocked or quarantined until it's compliant. And we have endpoint security. So endpoints such as laptops, smartphones, and tablets are common entry points for attackers. Endpoint security tools monitor and protect these devices from malware, phishing, and other threats. Let's zoom in on one of these tools, which is the packet filtering firewall. It is one of the most basic yet foundational types of firewalls used in most corporate environments. It acts as a network traffic gatekeeper, analyzing data packets based on defined rules and deciding whether to allow or block them. So when data is transmitted over a network, it is broken into packets, which are small chunks of information. Each packet contains the source IP, destination IP, the transmission protocol, and port number. The firewall checks each packet against a set of rules called an access control list, or ACL. If a packet meets an allow rule, it lets it through. If it meets a deny rule or doesn't match any rule, it's blocked. Let's look at an example. So imagine a company uses 4 firewall rules for its internal network. Rule 1 allows external users to access the company's web server securely via HTTPS. Rule 2 allows employees inside the network to browse the internet using HTTP. Rule 3 blocks external access to the internal database server for security reasons. And Rule 4 is the default deny rule. So this blocks all other traffic unless it's explicitly allowed in Rule 1 or Rule 2. This setup ensures that only legitimate traffic flows into and out of the corporate network, reducing the risk of unauthorized access or cyber threats. Of course, today's threats go beyond basic filtering. Attackers are more sophisticated and our defenses need to keep up. Let's explore some next level firewall technologies. We have stateful firewalls. Unlike basic filters, stateful firewalls track active connections. They understand the context of a network session and only allow packets that are part of a valid session. There are next generation firewalls which go beyond traditional firewalls. These perform deep packet inspection, identify specific applications, block malware, and enforce advanced security policies in real time. There are web application firewalls which protect public-facing websites and apps from attacks like SQL injection and cross-site scripting. These are threats that regular firewalls might miss because they happen at the application layer. And there are cloud firewalls. As companies shift to cloud platforms, cloud-native firewalls secure virtual networks and applications hosted on services like Azure, AWS, and Google Cloud. These firewalls are scalable and integrate well within the modern DevOps workflows. In today's corporate environment, businesses handle vast amounts of sensitive data, including customer information, financial transactions, and intellectual property. Protecting this data from unauthorized access, tampering, or theft is crucial. To tackle this, we have cryptography. Cryptography is the science of protecting information. It helps us keep data confidential, verify that it hasn't been changed, and ensure it only reaches the right people. You will see it in action when encrypting emails, securing websites, storing passwords, or verifying digital documents. To understand how cryptography works in a business setting, we will explore three core components: encryption, which protects data in transit and at rest; hashing, which ensures data integrity and password security; and public key infrastructure or PKI, which builds digital trust using certificates and keys. Let's start with encryption. Encryption turns readable data called plain text into unreadable data or ciphertext using a key and an algorithm. Only someone with the right decryption key can unlock it. This is crucial for things like transmitting data over the internet, storing files securely, and protecting databases and backups. There are two main types of encryption that we will come across in business systems: symmetric and asymmetric. Symmetric encryption uses the same key for both encryption and decryption. This means that both sides, say a server and client, need to have access to the same key. A widely used algorithm here is AES, or Advanced Encryption Standard. It uses a 256-bit key and is highly secure and efficient. We often use symmetric encryption to protect internal documents, secure stored files, and create encrypted tunnels for things like VPN access. With asymmetric encryption, we use a pair of keys: a public key for encryption and a private key for decryption. These keys are mathematically related, but knowing the public key doesn't reveal the private one. This is useful when we don't want to share a single secret key with everyone. Instead, we can publish a public key and anyone can use it to send us encrypted messages, while only we, with our private key, can read them. A popular asymmetric encryption algorithm is RSA, which is used in securing emails, SSL/TLS connections, and digital certificates. Now let's talk about something we interact with every day without even realizing. This is the SSL/TLS encryption, which protects our communications over the internet. This is what's behind the padlock icon we see in our browsers when we visit secure websites. It is also what powers the S in HTTPS. And here's how it works in a business scenario. When a customer visits your company website, their browser checks for your TLS certificate, which is issued by a trusted authority. The browser and server securely exchange keys using asymmetric encryption. After that, they use the faster symmetric encryption for the rest of the session. This hybrid approach protects sensitive data like payment details, login credentials, or confidential messages during the entire session. Now let's shift to hashing, which is a technique we use to verify data integrity and securely store information like passwords. Hashing takes an input, say a file or a password, and produces a unique fixed length value called a hash. A key feature of hashing is that it's one way. So we can't take a hash and reverse it back to the original input. Hashing helps with verifying that a file or a message wasn't altered, storing passwords securely, and creating digital signatures. If you send a file to a client, you also send its hash. When they receive the file, they hash it on their end and compare it. If it matches, the file wasn't tampered with. We never store passwords directly, we store hashes. We can use secure hashing algorithms like bcrypt or Argon2, along with salting, which is adding random data to the password to prevent attackers from cracking them easily. So if a system is breached, the hacker only gets hashes and not the actual passwords. PKI is the framework that makes all of this work securely in large systems. It handles creating and managing of keys, issuing digital certificates, authenticating users, systems, and software. PKI relies on certificate authorities, which are trusted parties that issue digital certificates. These certificates bind a public key to an identity, like a domain name or an individual's email address. Let's take a typical example. So a team member wants to send a sensitive email to a partner. They use the partner's public key to encrypt the message, and only the partner with their private key can decrypt it. To prove the email came from our side, we sign it with our private key. The recipient verifies the signature using our public key, confirming the email's authenticity and integrity. PKI is used in many places, securing emails, enabling HTTPS on our websites, validating software updates, and managing access to the key internal systems. Okay, that's it for this video. Let's look at the key takeaways. So first off, protecting our business data and systems is critical for trust and operations. The CIA Triad, which stands for Confidentiality, Integrity, and Availability, and the AAA Framework, which is Authentication, Authorization, and Accounting, are core security principles. Identity and Access Management, or IAM, is crucial for ensuring the right people have the right access. Multi-factor authentication, or MFA, adds a vital layer of protection against unauthorized access. Network security tools such as firewalls, IDPs, VPNs, and NAC are essential to defend against cyber threats. Cryptography, which includes encryption, hashing, and PKI, is the foundation of secure communication and data storage. And lastly, understanding common threats like malware, phishing, and insider attacks is crucial for their prevention.